It begins with a sound that does not happen. In the year 1905, in Bern, Switzerland, the air is still. A clock on a tower, a machine of gears and weights, is meant to strike. It is a promise made of brass and iron. But on this day, the promise is late. 2 minutes. Just 120 seconds, lost to friction, or humidity, or the simple fatigue of metal. In a small apartment nearby, a man lives by that clock. His mornings are built around its chime. The chime does not come. He sleeps. The pale amber light moves across the parchment-colored wall. It climbs from the floor to the edge of his bed. He wakes, not to the sound of the bell, but to the bright insistence of the sun. There is a moment of stillness, the peaceful void of a routine not yet broken. Then, the realization. He is late. The man becomes nervous. A quiet internal cascade begins. His movements, usually measured, are now hurried. He fumbles with a button. He spills a small amount of coffee, the dark liquid staining the beige wood of his table. He takes a little longer to get dressed. He leaves the house 5 minutes later than usual. 5 minutes, the wait of a few breaths. He stands at the edge of the street. The air is cool. The street is a path of warm gray cobblestones. He is about to cross. At the same moment, a banker settles into his new automobile. It is a marvel of new technology. He does not know that its brakes have a fault, a small, invisible problem. The man steps into the street. He does not see the car does not see him. Or rather, the car cannot stop. The impact is not loud. In this world, drawn in soft brown lines, it is a moment of sudden, final geometry. A body is struck, a life ends. This man is Albert Einstein. In this version of 1905, the one that ended in cobblestones, Einstein was meant to publish 4 papers, 4 ideas that would bend our understanding of light, of time, of energy, and of matter. They were to be the foundation of modern physics. But the clock was late. The coffee was spilled. The man is late. The papers are never written. The equations remain unsolved. Ghosts in the mind of a man who is no longer there. The world continues. But it is a different world. The innovations that would have grown from his ideas, they do not happen. The screens that glow with captured light. The semiconductors that allow us to think in silicon. The satellites that map the Earth and guide us home. GPS, televisions, laptops. They are never conceived. The mobile device, the computer, the tablet, none of them come into existence. The entire digital age is stillborn. This story, this very narration, does not exist. All because a clock in 1905 was 2 minutes late. This sequence of events, this chain of causality, is an illustration of something else, an idea known as the butterfly effect. It is a window into a larger concept, chaos theory. For many centuries, the world was explained through a different set of rules, the laws of Isaac Newton, the logic of classical physics. It was a comforting vision, a universe that operated like a magnificent, predictable machine, a clockwork universe. If the current state of any object was known, its mass, its speed, its direction, its future behavior could be predicted. An apple, loosed from a branch, will always fall. A planet, caught in the gravity of its star, will always follow its prescribed orbit. The lines were clean. The math was pure. The future was, in theory, already written. We simply had to learn how to read it. Stillness. Order. Certainty. A world where every cause had a clear, proportional, and predictable effect. But this deterministic vision, this perfect clockwork, began to show hairline fractures. Since the 1800s, mathematicians had found problems. Small corners of the universe that refused to be predicted. Systems where the equations became tangled, their solutions branching into infinity. They raised the idea that not all phenomena, not every cloud, not every turbulent stream, could be predicted by Newtonian laws. The belief in perfect certainty began to erode, but it was a slow, quiet doubt. It lacked a clear image. It lacked a story, until a meteorologist named Edward Lorenz made chaos theory a visible phenomenon. It all started in 1961. The world was deep in a new age of computation. Lorenz was working on a mathematical model to forecast the weather. He used a computer, a large beige machine that filled a room with its quiet hum. He would enter data, numbers representing temperature, humidity, atmospheric pressure, wind direction. His computer would take these simple starting points and draw a graph. A soft, brown line, tracing a path across a field of paper. It was a model of what the weather would be like. It was not always perfectly accurate, but it was very close to reality. It was a useful tool. One morning, Lorenz decided to verify some previous results. He wanted to rerun a simulation he had already completed. To save time, instead of starting the entire sequence from the beginning, he decided to start it from the middle. He stopped the computer. He looked at the printout from the previous run, and he typed the numbers in himself. He entered the temperature, the pressure, the wind speed, all taken directly from the earlier graph. He restarted the machine, and he went to grab a coffee. This is the pause, the moment of stillness, like the 2 minutes the burn clock was late. A man walks down a hallway. The machine hums. The light in the office is a diffuse, warm gray. The world, for a few minutes, is still the predictable Newtonian world. The equations are running. The coffee is poured. The future is being calculated. When Edward Lorenz returned to the room, the graph was waiting. He looked at it, and it was wrong. It was incredibly different from the original simulation. He looked closer. At the beginning of the graph, the new line traced the old line almost perfectly. The two paths started as one. But then, in the middle, a tiny, almost invisible separation began. The new line drifted. It pulled away from the original, just a fraction. And then, with gathering speed, it presented a completely different trajectory. Two separate futures, two completely different weather systems, born from what should have been. Number two, the exact same data. He was surprised. He was confused. He assumed a mechanical error, a faulty tube. He checked the numbers. He compared the numbers he had typed with the numbers stored in the computer's memory. And he found it. The difference. The computer's memory stored the numbers in 6 decimal places. For example, 0506127. The printout, the paper he had read from, Hobland, had rounded those numbers. It only showed 3 decimal places, 0, 506. So, the number he had entered was 3/10,000ths, less than the number used by the computer. A difference of 0.0000127. A difference so small, it was considered statistically irrelevant. A rounding error. Lorenz wrote later that this difference, which altered the entire future of the weather, is equivalent to a particle of dust on the Eiffel Tower. It is one less feather in the weight of a duck. In that moment, standing in front of the humming machine, Lorenz understood. This was not an error. This was a discovery. This was not a special case. He deduced that there were other systems, many other systems, in which tiny, infinitesimal differences in the starting conditions produced, over time, monumental, catastrophic changes in the outcome. The systems were sensitive. They were so sensitive that they amplified the smallest, unmeasurable whispers of change into dramatic, unpredictable futures. This was the death of the Clockwork universe. This was the birth of chaos. This was the moment that gave rise to the metaphor. The idea that the flapping of a butterfly's wings in Brazil, a tiny, almost weightless disturbance in the air, could, in theory, set in motion a chain of atmospheric events that would build and cascade and amplify until it sparked a tornado in Texas. It meant that prediction, true long-term prediction, was impossible. Not because the laws of physics were wrong, but because we could never, ever, measure the starting conditions with enough precision. Even if we have a good idea of how the universe works, there are no measurements that allow us to determine the exact position and the exact speed of every single atom in the universe. And this inaccuracy, this fundamental limit to our knowledge, this 0.0000127 makes long-term prediction a fantasy. But chaos is not the same as disorder. This is the most important and most beautiful part of the discovery. Although chaos makes prediction difficult, the universe is not random. Effects still follow causes. The system is still deterministic. The butterfly causes the change. The problem is, we can never see all the butterflies. And no matter how chaotic it may seem, a system, like the weather model Lorenz built, always follows a trajectory towards a certain point. It is bounded. When Lorenz let his computer run and plot its chaotic path, the line it drew, the line that represented the chaotic, unpredictable weather, began to draw a shape, a pattern. The trajectory created a pattern that resembled the 2 wings of a butterfly. It is called the Lorenz attractor, a strange attractor. It is a visual representation of chaos, a line that loops and crosses and turns, but never repeats itself, and it never leaves a defined boundary. It is a map of infinity contained within a finite space. It is order, hidden inside the unpredictable. Understanding these patterns, understanding that the world is not a clock, but a bounded chaos, Brastablent, has practical applications. It changes how we see the world. In the stock market, it reminds us that a slight fluctuation, A single, small trade, a rumor, can be amplified by the system and cause a crisis in the entire market. And that is why we cannot speak of predictions, but only of probabilities. In the human body, it allows us to understand the chaotic behavior of a heart. With cardiac arrhythmia, the heartbeat is not random. It is following a strange attraction, a pattern of chaos. Understanding that pattern helps us find new ways to guide it back, in fasten, to a stable, simpler rhythm. Even in human behavior, the butterfly effect can be used to analyze social phenomena. We can see how a wave of trolling, or a storm of social outrage, can be triggered by a single negative comment. One small act of malice, one tiny input, amplified by the sensitive, connected system of a social network, until it becomes a destructive, unpredictable force. Our universe continues to obey the laws of cause and effect. The sun will continue to rise every morning. The simple systems. The apple falling from the tree. The planes we build, they will keep flying. Classical physics still works for simple things, but chaos theory introduces an element of profound uncertainty into our reading of the universe. It reveals the limit of our knowledge. It tells us that we live inside a system so complex, so interconnected, so deeply sensitive, that we cannot and will not ever see the whole picture. We are back in 1905 with the man on the cobblestones. We are back in 1961 with the man watching the graph. We are all, always, living in the space between the two lines. The future that happened and the future that could have been. Separated by the weight of the present, by 2 minutes, by a single cup of coffee. It is the beautiful, terrifying, and humbling truth of the world we inhabit. A world where everything is connected, but nothing is certain.